In the last lecture, when I completed the 2 problems on rotational kinematics about a fixed axis with constant acceleration, constant angular acceleration that is, I implied that there are directions associated with vectors associated with the rotational quantities. How can the rotational quantities be vectors? Well, let's begin with angular position. Let's say that angular position is a vector. If angular position is a vector, then it should obey the basic mathematical properties of vectors that we've already examined. So, for example, say the commutative property of vector addition. So if angular position is a vector, does it obey the commutative property? Let's begin by asking that question. Okay, is angular position theta a vector quantity? Okay, if so, it would obey the commutative property of vector addition. In other words, let's say that we have a theta 1, which I'll draw as a vector, and I add that to a theta 2. Okay, if angular position is in fact a vector, then the resultant of theta 1 plus theta 2 should be the same thing as theta 2 plus theta 1. Like so. So let's see if in fact, if angular position is a vector, it obeys the commutative property of vector addition. Here's how I'm going to demonstrate that. I'm going to do so with this textbook. And what I'm going to do with this textbook is I'm going to rotate it through 2 90-degree rotations. Let's say that theta 1 looks like this. And let's say that theta 2 looks like this. So then therefore, on the left-hand side of the expression, theta 1 plus theta 2 looks like that. However, now I'm going to reverse the order of addition. Watch this. Now I'm going to do theta 2 plus theta 1. Is this the same thing as what I did earlier? Once again, what I did earlier was the following. Theta 1 plus theta 2. But now what I'm doing here on the right-hand side of the expression is theta 2 plus theta 1. Is it the same? No, it is not. So then therefore angular position cannot be a vector because it does not obey the commutative property of vector addition. So then therefore, the answer to this question is no. As you saw in my demonstration, the commutative property is not obeyed. So then therefore angular position theta cannot be a vector quantity. However, what I'm now going to do is I'm going to make the angle smaller. When I did my demonstration a few minutes ago, I did it with 2 90-degree rotations. Now let's make the angle smaller. Now, however, make the angle smaller. So now watch this. Once again, I'm going to say a theta 1 is a rotation like that, and a theta 2 is a rotation like that. Once again, I'm making the angle smaller than 90 degrees. So watch it again. Theta 1 plus theta 2. Okay, now I'm going to do theta 2 plus theta 1. And what do you notice about the orientation of the book with these 2 different vector additions? Now the sum, the resultant of the 2, is starting to look the same. So watch it again. Theta 1 plus theta 2, and then secondly, theta 2 plus theta 1. Notice that the resultant of the 2 is starting to look the same. In fact, if the rotations are infinitesimally small, then yes, the resultant is the same, and then therefore the commutative property of vector addition is obeyed. So now what I'll do are 2 really small angles to illustrate this. So here's a d theta 1, and here's a d theta 2, and then add that together, and now we'll go d theta 2 plus d theta 1, and it basically looks exactly the same. So then therefore angular position is not a vector, but the infinitesimal change in angular position is a vector. So however, when we make the angle smaller, note that d theta 1 plus d theta 2 is equal to d theta 2 plus d theta 1. The commutative property of vector addition is obeyed. Therefore, not angular position theta, but infinitesimal change in angular position d theta is a vector. Okay, now the question becomes, what is the direction associated with that vector? When talking about position, velocity, and acceleration as translational quantities back in chapter 2, it was obvious what the directions meant. Positive direction or negative direction, and so on and so forth. However, what about the rotational quantities? What is the direction associated with them? This is your first introduction to a rule that is used throughout the scientific community and the engineering communities worldwide. As we'll see later on, and including in this unit, a number of different physical phenomena obey this mathematical rule. This is one of the reasons why we use it. The rule is called the right-hand rule. Draw my marker. Okay, so now, what is the direction of d theta? Well, it obeys the right-hand rule. Let's say, for example, that we have a turntable. My turntable here, which I still have on my desk from earlier, and now let me go ahead and turn this on, and it spins up like so, in this manner. Okay, it's rotating in this direction like so in my demonstration. Now notice that I used my right hand when I did that a few moments ago. I took the fingers in my right hand and I curled them in the direction of the rotation, and then my thumb points straight downwards. So in this simple demonstration, this then means that the d theta vector points in the direction of my thumb of my right hand by definition. It points downwards like so in this simple demonstration. This is an illustration of the right-hand rule. What you do with your right hand is you take the fingers in your right hand and you curl them in the direction of the rotation. And then the direction that your thumb points, that is then, by definition, the direction of d theta. So let me go ahead and draw it here on the board in the following manner. When I did this demo a few moments ago, my thumb was pointing downwards because the rotation was like so, but let me just draw it in this manner here on the board. Okay, so now here's three-dimensional space like so, and then here's the XY plane. Okay, let's say that the turntable is rotating in the XY plane like so. And the rotation is in this direction. So you then take the fingers in your right hand, and go ahead and do it while you're sitting at your desk. In order for you to understand how to use the right-hand rule, you have to sit there and use it. So go ahead and do this as I demonstrated. You curl your fingers in your right hand like so in the direction of the rotation, and then the direction that your thumb points. That's then the direction like so of the angular position, d theta, like so, the infinitesimal change in angular position. This then gives us now how we define the direction associated with angular velocity. Okay, angular velocity now, as a vector quantity, is equal to change in angular position with respect to time. So then therefore, because d theta obeys the right-hand rule, so does omega, the angular velocity. So the angular velocity vector also points upwards on the diagram like so. So right here in green, I'll just give it its own vector like so. Right here is the angular velocity vector like that. Okay, and then what about angular acceleration? Okay, angular acceleration is the derivative of angular velocity with respect to time. So the direction of the angular acceleration vector alpha is always in the same direction as the change in angular velocity vector d omega. Okay, now let me reference the two examples that I did in the previous lecture. The first example involved an automobile engine that was spinning up, and then in the second example, it involved a flywheel that was spinning down. Let's examine those two problems here just qualitatively and understand the directions associated with the rotational quantities. So now let me go ahead and do some erasing here like so. Okay, so first of all, we had that automobile engine example. If you recall, this is when the automobile engine was spinning up from 1200 to 3000 RPMs. So just qualitatively, here's basically what was happening in that problem. Okay, once again, I'm going to draw a three-dimensional space like so. Okay, and then right here we'll say is the portion of the automobile engine that's rotating. Once again, we'll say that the rotation is in this direction, like so. Okay, and then initially, let's say it's rotating at 1200 RPM, and this then represents omega naught, the initial angular velocity. So then therefore, we have a rotation like so, using our right hand, and the direction of my thumb then therefore is the direction of the initial angular velocity vector. So right here we'll say is omega naught. Okay, and then the thing spun up from 1200 to 3000 RPMs. So this then means that the final angular velocity vector, omega, is bigger in magnitude than omega naught. So then therefore at the end of the problem, after it's spun up, once again, draw a three-dimensional space like so. Here's the portion of the engine that's rotating. The rotation is once again like this. It's rotating at 3000 RPM, however, therefore the final angular velocity vector omega is bigger in magnitude than omega naught. Once again, it obeys right-hand rule and it points in this direction like so. Like this. Okay, so now where on this diagram is the change in angular velocity vector delta omega? Well, it obeys the tail-to-tip method of vector addition. So initial plus change is equal to final. So now just look at the green vectors themselves. Which direction does delta omega point? Well, off to the side, we have right here, omega naught. And now we'll add to that like so, delta omega, which points upwards in this description. This then gives us the final value of omega like so. So because we defined omega naught and omega as positive numbers, I wrote them down that way in the example. This then means that what I'm implying is that up with my right hand thumb is the positive direction. Therefore, delta omega here points upwards on the diagram. It points in the positive direction. Therefore, the angular acceleration alpha vector points upwards. It's positive on the diagram. Remember that angular acceleration is change in angular velocity with respect to time. So the direction of the delta omega vector is always the same as the direction of the alpha vector, the angular acceleration. So in this problem, the angular acceleration points upwards on the diagram like so, and it was a positive number. I just didn't say it as such, of course, in the example itself. Okay, and then we have the second example involving the flywheel, and the flywheel, remember, was slowing down in that problem. It ultimately came to rest. So now here's just a qualitative description of what happens when you have an object that is spinning down. Okay, once again, I'll use this tail-to-tip method of vector addition expression here to illustrate the directions associated with the angular velocity vectors. Okay, so here's the flywheel example. Now in the actual example, if you remember, the object spun down to rest. Well, let's just see what happens while it's slowing down. That's good enough. So while spinning down. Okay, begin first of all, once again, by drawing three-dimensional space like so. Let's say here's the flywheel rotating in the XY plane. Once again, let's say that the rotation is in this direction. Okay, therefore the omega naught vector points upwards like so. Okay, and then it's slowing down as time goes on in this problem. So then therefore, as it does slow down, let's say a moment later, so a bit later, while it's spinning down. Here's our flywheel, rotating in the XY plane. Okay, and now it's still rotating in this direction like so. It's just slowing down as it does. Therefore, the magnitude of the final angular velocity vector omega is smaller than the initial angular velocity vector omega naught. Therefore, right here on the diagram, we'll say, is the omega. And now use the tail-to-tip method of vector addition to describe the delta omega, and it looks like this. So right here is the omega naught, and then we add to it like so the delta omega, which points downwards in this situation. This then gives us the final value of omega like so. So initial plus change is equal to final. So the delta omega vector points downwards in this description. Therefore, the alpha vector, the angular acceleration vector, points downwards as well. That's the negative direction here by definition in the problem. Once again, in this problem, we were calling upwards on the diagram the positive direction, even though I didn't state it as such during the actual example. So the alpha vector points downwards like so, hence the negative sign we saw associated with the alpha vector. For now, think of the positive direction and negative direction associated with the rotational quantities as mathematical bookkeeping, and all that mathematical bookkeeping obeys the right-hand rule. Is there actually, however, anything pointing, for example, in this direction like so, as the wheel rotates? No, there isn't. So for this reason, sometimes, particularly in the case of these rotational quantities, these rotational vectors are sometimes referred to as pseudo-vectors for that reason. However, as we get deeper into rotations, we'll see physical phenomena that obey the right-hand rule, and especially in the next semester when we get to magnetism. Magnetism obeys the right-hand rule as well. Once again, this is one of the reasons why we use it throughout the scientific community. Okay, let me go ahead and conclude this video with another demonstration, however. In order for me to show you this demonstration, however, I've got to tilt the phone to the side, so bear with me here as I do. All right, so I'm going to shift my phone like so, and I have a pulley there that's attached to my vertical pole. Okay, and then draped over the pulley, I've got this string right here. And then I have two small weights attached to the string. There's a little bit more weight here, however, than there is here. Now, recall earlier in an Atwood's machine situation that we looked at back in Dynamics in Chapter 4, we ignored the rotation of the pulley. Now let's go ahead and take it into consideration. Watch what happens, for example, when I release the objects from rest. Like so. You could see, for example, that the pulley rotates in that direction. Let's call this direction, by definition, the positive direction. So then therefore, if I start at rest, omega naught is equal to 0, and then I release and time goes by like so, and I have a final value of omega in this direction. Therefore, the delta omega vector points in this direction. Therefore, the angular acceleration vector, alpha, points in this direction. Here's how you can keep this straight in your head. Think of it in terms of vector addition. So we start off with omega naught as a point equal to 0. And then I add to that the delta omega vector, which points in this direction like so. Therefore, that gives me a final omega vector, which points in this direction like so. So it's omega naught, which is 0, plus delta omega is equal to omega. Therefore, the alpha vector points in this direction. Once again, we think of that as the positive direction. Okay, now watch what happens if I initially release the objects while I'm taking this object and moving it upwards, like so. And then we look to see what happens immediately after I release the object. Well, when I released the object, the pulley was rotating in this direction. So the omega naught vector points in that direction. We already know, however, that the angular acceleration vector, alpha, points in that direction. So then therefore, delta omega has to point in that direction. This then means that the final value of omega is bigger than the initial value. Once again, you can think of it in terms of the tail-to-tip method of vector addition in the following way. Watch this. Omega naught plus delta omega is equal to omega. So then therefore the alpha vector still points in that direction. These first two scenarios are fairly easy to wrap your head around. However, watch what happens in this last scenario when I take this object here and I initially move it downwards and then let go of it. Okay, watch this. Like so. You can see that when I take this object here and initially move it downwards and let go of it, that the pulley is actually rotating in this direction like so. So then therefore, the omega naught vector points in that direction. However, the whole time, the alpha vector still points in this direction here. And you would then add the vectors together in the following way. Let's see what happens, for example, when I go from here to here, when the pulley is rotating like that for a final value of omega. Now you have to think of it like this. Watch this. Omega naught plus delta omega is equal to omega. Therefore, the whole time, the alpha vector still points in this direction. Make sure that you understand this demonstration in terms of the directions of these vectors. Make sure that you understand the directions of the vectors in the two kinematics problems that I've already completed.